Suppose we're given a polygon in three-dimensional space, whose sides all have equal length, but whose joints are allowed to rotate freely. What can we say about the possible shapes of this object? In this problem, we consider two polygons to be the same if we can go from one to another by rotating and translating without changing the shape at all. Although this seems like a simple question, the answer combines ideas from many areas of mathematics and is an active topic of research today. If the polygon has three sides, this question isn't very interesting. Since all the sides have equal length, we always have an equilateral triangle, so there's only one possible shape. However, if we have four or more sides, there are many distinct configurations. For instance, if we restrict our attention to equilateral quadrilaterals in the plane, we can form any rhombus we want. And we can make more complicated shapes if we allow the quadrilateral to lift out of the plane. Therefore, we want some way to classify all equilateral quadrilaterals systematically. In mathematics, we can solve these sorts of classification problems by constructing what is known as a moduli space. The moduli space is a space whose points correspond to different configurations. In other words, each point of the moduli space corresponds to a particular quadrilateral, so that when we change the point, we change the shape of the polygon. As such, we can rephrase our original question in the following way. What is the moduli space of equilateral quadrilaterals? This is a difficult problem, and I have no shame admitting that it stumped me when I first learned it. However, there is an intuitive way to solve it if we look at the geometry in just the right way. One way to distinguish between quadrilaterals is to consider the distance between a pair of opposite vertices. By changing the distance between these points, we change the geometry of the quadrilateral, which means that they are genuinely different. However, there are many different quadrilaterals which have the same diagonal length. So in order to specify a quadrilateral uniquely, we consider the two triangles formed by the edges and the diagonal, and compute the angle between the faces of these two triangles. By specifying an angle and a diagonal length, we specify a quadrilateral uniquely. From this, we can see that the space of equilateral quadrilaterals is two-dimensional, which is not at all obvious. As a brief aside, the diagonal length angle pair are known as action angle coordinates, and they have some important connections to the underlying symplectic geometry at work here. Back to the main story. If we look at the space of all possible diagonal lengths and angles, we get a picture which looks a little bit like this, where a point in the hemisphere corresponds to a quadrilateral, and by changing the quadrilateral, we change the point in the hemisphere. In this picture, the height of the point gives the diagonal length of the corresponding polygon, and the azimuthal angle gives the angle between the two triangles. The reason that the surface closes up at the top is that there's only one quadrilateral whose diagonal has length 2, which is a line segment which looks like this. As such, it is more accurate to draw the moduli space as a hemisphere rather than a cylinder. So this is our first guess for the geometry of the moduli space. However, this picture isn't quite right. The reason for that is if we consider points near the boundary of the hemisphere, this quadrilateral and that quadrilateral are actually the same, just rotated by 180 degrees. So even though they correspond to different points in the hemisphere, they're actually the same shape. To fix this problem, what we need to do is glue together the boundary of the hemisphere in the following way. When we do so, we get a picture which looks like this. From this, we find the surprising fact that the space of all possible quadrilaterals is topologically equivalent to a sphere. That is to say, there's a one-to-one correspondence between equilateral quadrilaterals and points in a two-dimensional sphere. However, it is not a round sphere, and actually has three cone points, which correspond to quadrilaterals, which lie in a single line. And taking into account the various symmetries of the space, the geometry actually looks something like this. This picture has a bit of a backstory to it. Earlier this summer, I made an initial version of this video and said that this shape was my best guess for the geometry of the moduli space. However, I expected the actual geometry to be fairly complicated, since the computations needed to understand it were really involved, even with the help of Mathematica. So I made this graphic in Blender and figured I'd be happy to be proven wrong, since it would mean that someone had figured out what the geometry actually looks like. About a week after posting the video, I got an email from Lyle Ramshaw, who had just written a paper on equilateral pentagons. He was curious about the structure of the singular points, and we discussed what was needed to better understand their geometry. Within 2 weeks, Lyle had written a formidable Mathematica notebook, which gave an accurate picture for the entire moduli space. And the final answer turned out to be much simpler than I could have ever imagined. It turns out that my original picture is pretty close to what the space actually looks like, but the geometry has some remarkable features which are completely unexpected and really spectacular. Unfortunately, in order to describe the shape in more detail, I would need to cover some background in complex differential geometry, since the moduli space is not only a symplectic space, but is also a Cahill manifold away from the singular points. Covering these topics would double both the length of this video and the number of math courses needed to understand it, so I'll have to leave that for a future video. There's one aspect in which the original hemisphere picture is an accurate representation of the moduli space, even though it doesn't preserve the overall structure. When you use diagonal lengths and angles to specify quadrilaterals, this preserves areas in the moduli space, which makes it useful for studying random polygons. In other words, the hemisphere picture is analogous to an equilateral map for the Earth, which preserves the size of countries, even though it distorts distances and angles. There's much more that can be said about spatial polygons, which could easily fill a series of lectures. For instance, it's possible to build a similar moduli space for polygons with more sides, or when the side lengths aren't all equal. However, the geometry gets more complicated as we increase the number of sides, so we won't discuss those spaces in this video. The study of these spaces also combines ideas from many areas of math. To give just one example, Jason Cantarella and Clayton Shonkwiler use the geometry to study random walks which start and end at the same point. In fact, they even use the action angle coordinates to create a Markov chain Monte Carlo algorithm which samples random walks efficiently. Even more surprising, the study of these moduli spaces have applications in chemistry and biology, since polygons in space are a simple model for complicated molecular chains, and in particular DNA. It was very surprising to me to see something which originated in the abstract worlds of symplectic and algebraic geometry show up in applications. But I think that's part of what makes spatial polygons so fascinating. Not only is this a beautiful and fairly accessible example of a moduli space, but it's one that has connections throughout mathematics and science. I'd like to thank Kevin Rosales, who wrote most of the music for this video, and Alex Wright, who gave a series of lectures where I learned this topic. Alex had the idea of making spatial polygons out of straws, which gives a great, hands-on way to explore the geometry. I'd also like to thank everyone who made suggestions for improvements to the earlier version of this video. If you are interested in experimenting with the moduli space, in the description there are links to some of the GeoGebra files used in this video. This video was funded in part by a collaboration grant from the Simons Foundation.